Okay, taking a look at number 4 on the 2004 ACS exam. So what we have here is start off with a alcohol, and we have 4 steps. Of course, you're not expected to know the mechanism for these, but you are expected to be able to show the product, what the product will end up being. So the first thing you could do is look at this first reagent, PBr3. What does PBr3 turn an alcohol into? Br. So you kind of got to know that. Even if you didn't know that, you could look at number 2, say, okay, well, PBr3, I have no idea what that is. But then if you look at number 2, you see magnesium, just Mg. Now, hopefully that tips you off, because the only time you've ever used magnesium like that is when you already had an alkyl halide, right? So maybe that would tip you off, right? Hopefully that would tip you off. So maybe we thought magnesium, that should have tipped us off. Okay, well, that's the only time we have that is when there's a bromine. So OH with PBr3 definitely turns into OH and PBr3 turns into a bromine. One thing to do is also to number our carbons quick. So out of these first 2 steps, hopefully we'll see that we'll have essentially a Grignard reagent. We'll have a Grignard. 1, 2, 3. Now let's say we even didn't understand what this was. If we got to 3, that's an epoxide. Or no, is an epoxide an electrophile or nucleophile most of the time? It's an electrophile. The carbons of the 3-membered ring are pretty delta plus, and they're also pretty strained. So whatever this epoxide is going to react with is probably going to have to be a nucleophile, right? So even if we hadn't, right, epoxides are good ways to add carbons. So we're going to add how many carbons with this epoxide? 1, 2. So let's number those. 4, 5. Does it matter which epoxide which carbon I go after? 4 or 5? No. Grignard is a nucleophile. Let's go after 4. So I made a new bond between. I always like to number my carbons. Don't want to get lost. 3, 2, 1, 4, 5, and then O minus is there. And then the last step would be H3O plus, right? Would be this O minus reacting with acid. That's going to make the alcohol. The whole big thing here is, too, if you have an idea, right, if you had any idea about any of these reagents, right, at least the first 2, should you have ever looked at have I looked at the answers yet? Do not look at the answers. This is one of those questions where you shouldn't look at the answers. If you have no clue, then you look at the answers. But stop. Be fair to yourself, right? And if you do look at the answers, what are some things you need to think about? Numbers of carbons, right? All of a sudden, there's a reagent with 1, 2, 3, 4, 5, 6, 7 carbons, and then it's reacting with something with 2 carbons. So I would guess, at the end of the day, how many carbons would be in the product? 9, right? And then I look at the answers, and only one of them has 9 carbons. So even easier, like only one of them has 9 carbons. So the answer for this one is D, but it's also the only one that has 9 carbons. So, right, so if worst case scenario, you had no clue, right, keep your wits, right? It's something with 7 carbons rather than something with 2 carbons. Well, worst case scenario, I have something there that has 9 carbons. I'll pick that one. That's a good choice. So number 13 is asked as the weakest base, but this question really is, do you understand hybridization? Right, and then because of that, how reactive lone pair reactivity. And then also really aromaticity as well, which has to do, of course, with, right, resonance is going to be built in there too. So that's what this is really asking us. Right? It's asking for the weakest base. Would that be the most reactive or least reactive lone pair? The least reactive lone pair, right? Which one's the weakest base? So let's take a step back and see if we can mark which is which. So first I would do is draw in lone pairs, right? Or at least recognize where the lone pairs are at. and I'm looking for the weakest base. So it's a kind of a weird one, right? You're used to looking for maybe the most reactive. Now this is going to be the least reactive. So which one is it? Do we have a gut feeling right off the bat? So this lone pair is in an sp3 hybridized orbital. That lone pair is in an sp2. That lone pair is in an sp2. That lone pair is in what hybrid orbital? Careful. It's in a p. This one is also in a p. Why is this one in a p and why is this one in a p? Because they're part of the aromatic system. They can do resonance, right? Notice, right? This nitrogen, that lone pair is sp2 because it has a pi bond. What kind of hybrid orbitals make up pi bonds? P orbitals. Show me the p orbitals. Haven't done that in a long time. Right? If you can be in a p orbital and that lets you have resonance, you'll be in a p orbital. If you're part of an aromatic system, are you going to be very reactive? No, right? Because aromaticity, what do you guys know about aromaticity? It's hard to break because it's very stable. So which one's going to be the least reactive? So we know now, it's going to be one of these. It's going to be one of these two, right? Which one's going to be the least reactive then? So if it's A or B? B, exactly. Because A still has this one, right? This lone pair is not reactive, but this molecule still has that lone pair. So the weakest base then will be the lone pair that's in an aromatic system. Right? Because if you're in an aromatic system, you're sharing your electrons. You don't want to let your electrons react. Which one of these is the most reactive? Right? So this is how you turn the question on its head. Right? You look at this and say, okay, that question was about the weakest base. Another way they could ask this would, right, to get at these same ideas would be, say, which one's the most reactive base? Which one do you think is the most reactive? A, B, C, or D? C. Why C? That's right. I would guess C, because it's sp3 hybridized. Those electrons are farther from the nucleus, right? So that makes them more reactive. Now be careful though, because there's some sterics here as well that could be a problem, right? Maybe if you get really bulky, then there's some sterics that might be getting in the way. But right, I like your logic about the hybridization state making a difference for reactivity. Good. Number 8, this is a Newman projection question. It says arrange these conformations in order of internal energy. List the highest energy conformation first. So part of this is reading comprehension. Which one do they want first? The highest energy one. Right? So you got to remember that right off the bat. Highest energy one. Now you look at these and you have 4 types. The other trick here, not trick, but yeah, kind of trick. If you look at the answers, good luck. It's going to screw you up. Right? Don't look at the answers. It's all over the place. There's greater than signs. Oh my God, right? They want the highest energy one first. So if I look at these, which one of these is the highest energy and why? 4. Why 4? What's that called when they're like that? Eclipse, right? So be careful. They might use the term eclipse, right? So it's not just enough to know, oh, they're the ones that are on top of each other. Like that's not going to be written in this test like that, right? They're going to use the term eclipsed, which we've used, right? So be ready for that term too, right? So this is really about Newman projections, right? And the energies associated with them, right? We did a lot of rotating with Newman projections and taking them from wedges and hatches and doing that kind of stuff last semester. Okay, so 4 is the highest. So I'd write my answers. Okay, 4 would be 1. What else would be next, do you think? Knowing what you know about eclipsed conformations are higher in energy, so the second one would be the next one, right? Yep. Now what would be the third one? Which one? 3. Why 3? Because the larger groups, highest priority, the larger groups are next to each other, right? They call this gauche. You'll see this term maybe. Gauche. They're 60 degrees away from each other. That's a 60 degrees away. That's a term you might see, gauche, right? Versus the 2 big groups being 180 degrees away. So the next one would be 3. and then 1. Once we have that, then we go look at the answers. Then we go look at the answers, right? Then we go look at the answers. If you have no clue, you could also look at it, right? If you look at this, you're like, I like to think you'd understand this, but right? So why would you, if you had no idea, you'd want to look for answers that are the same. Like, so in this case, B and C both start with 4. One of those is the answer. For sure. One of those is the answer. If I look at that and I say, right, just test taking skills, I would like to try to take these tests and not read the questions, see how well I can do. Right, some level is just, right, it's B or C. Right, because it starts with 4, so you got a 50-50 shot then right at the bat. If you have no clue. Now, I'm not advocating that. Right? I want you to do well. You need to do well. But, right, again, this is like keeping your wits about you. Keeping your wits about you. Look at the answers and analyze them if you have to. That's not your first go-to, but if you have to, then you can go there. So number 15, first thing you need to do is check your reagent sheet. And these would come up. Potassium fluamide and potassium hydroxide. Hope those are correct, right, guys? Got that right? So what's it going to do? What's it going to do? Again, if you look at this, how many carbons are in this starting material? 4. Very good. 4. This is an alkyl halide, right? Maybe you recognize this as the Gabriel synthesis, and that should tip you off as about amines. Maybe, maybe not. Right? So maybe you recognize this as the Gabriel synthesis. Maybe you don't. If you recognize it as a Gabriel synthesis, you know right away it makes amines. Then that makes this question really easy because there's only one amine in the answer. That's A. What if you don't recognize those reagents? Then you can look at the IR, right? You can look at the IR and the NMR. What does the IR show you? There's a peak, there's a doublet way around, there's a doublet in the IR, right? It looks like a kind of a fang way down around 3200 wave numbers, right? If you look at your sheets, you recognize that as being indicative of an NH2. Not an OH, right? OHs are big and broad and fat, but an NH2 has those 2 fangs because there's 2 H's. And that would already give it away too. Because then you could go down and look at the answers and say, well, there's only one amine. And alcohols have really broad OHs, right? So the answers are, there's an amine, there's 2 alcohols, and an amide. So just look, you don't even look at the NMR, guys. Just look at the IR. Do you see a peak? Do you see a broad OH band? So can it be an OH? No, so we've already eliminated that. Let's say you forgot about the NH2 doublet. An amide has what kind of stretch that an amine doesn't have? What's an amide? Under the broad group of, what's the name of the mountain? Carbonyl. Where are carbonyls at, generally speaking? Where are they at? 1700. Do you see any strong bands around 1700? No. So it can't be that either. We haven't even looked at the NMR. Right? We don't have to look at it even. It's just almost superfluous. Right? The IR gives you all the data you need. So the answer is A. Number 14. The question asks, which of these is optically active? So opt active, which is just a fancy way of saying which of these, right, has asymmetric carbons, rotates plane polarized light, right? So this is a R or S or maybe a chiral molecule kind of question. Do you understand chirality? And also, do you understand this term meso? That's what this is getting at. That's what this question is about. Is do you understand, right, when a carbon has 4 different things bonded to it, that's sp3 hybridized, right, would that be RS? And then do you understand, is a molecule chiral, and something about meso compounds and their internal mirror planes? So only one of these is optically active. So the real big question here that they're trying to get at, see if you understand, is this idea of a meso compound. A meso compound. Everybody remember what a meso compound is? What's a meso compound? You're a meso compound. You have a meso compound is a compound that has asymmetric centers, right? Like your hands are asymmetric, right? They're mirror images of each other. But within the molecule itself, there's an internal mirror plane. So meso compounds are achiral, right? They're achiral. If you have an internal mirror plane, you're achiral. And if you have asymmetric centers and you have an internal mirror plane, that's called meso, and you're achiral. You are a meso compound. Your right and left hand are asymmetric centers, but you have a mirror, right, an internal mirror plane, right? You can divide in some level, not your insides, but, right? You can divide yourself in half. You have an internal mirror plane. So we want to look for molecules, right, in this case, that are optically active. So we want to look for the ones that do have mirror planes because they will not be optically active. So which ones have mirror planes? You could cut down the middle and it wouldn't matter. They'd A and B. Yep. So if you look here, if you cut this down the middle, right? These are going down. Right? If you look down this molecule, right? The right and left halves would be the same. If you did the same thing here, right? If you looked down this molecule, you could cut it in half, and the right and left halves would be the same. Same deal here. If you cut this molecule in half, right? Well, also, that would also be the same, but here's a good question. Is that an asymmetric center? No, why not? It's not bonded to 4 different things, right? Chlorine and bromine are different, but are these 2 carbons the same? They are, right? So this one couldn't be actively active anyways, right? So what's that leave us with? D, right? D is the one that's optically active because it doesn't have that mirror plane. So D is the one. So how are they going to re-ask? How is this question going to be re-asked in a different way? They're going to give you all the compounds are optically active and say which one's not. Which compound is not optically active? That's what they're going to ask you. Right? That's the other way. The way to turn this around. That's what they'll do. Right? That's the other kind of question we'd ask. So make sure you're thinking about that too. Right? Understand what meso means. All right. Number 24 asks us, which aldopentose yields an optically active product upon reduction with sodium borohydride? So the first thing you need to look at, so I haven't filled these in, the first thing you need to know is what does sodium borohydride do to an aldopentose? Right? What is sodium borohydride? What is it? What kind of reagent is it? It's a reducing agent, right? It has H minus. So what are these things it's going to react in? All of these is going to react with the aldehydes in all of them. It's going to turn in all the OHs, right? So that'd be the first thing. These are all going to be, not that, they're going to be OHs. The other part of this question, what they're asking you is, again, they want to know, do you understand what a meso compound is? An optically active, right? Which is a way of saying, right, does it have asymmetric centers, but does it not have a mirror plane, right? If it has a mirror plane, then it's meso and it's not optically active. So let's start filling in these OHs and see if you can start to see which of these is going to have a mirror plane and which one is not. Right? They're looking for the one that's not, that is optically active, so it does not have a mirror plane. Which of these is optically active and doesn't have a mirror plane? So start looking for that symmetry. So things that are optically active usually don't have symmetry, right? Because if you have symmetry, you probably have a mirror plane. So which was it going to be? A, B, C, or D? Which one is it? It is B. So if you look, mirror plane here, cut down the middle. Mirror plane here, if you cut down the middle, right? The OHs are mirroring each other. Mirror plane here, if you cut down the middle. This one doesn't have that. This is the optically active one. Find those mirror planes, right? That level of symmetry. All right, so this is number 52. Again, this is a mechanism question. They ask what best represents a step in the mechanism for a saponification of ethyl acetate. So they're asking you really, do you know what, so you don't have to know this word, but saponification means right? Turning essentially an ester into an acid, saponifying it. Now, you may have heard that before when they talk about biodiesel, they saponify that, or that kind of stuff, or fatty acids get saponified. So it's just basically turning a carboxylic acid, or turning an ester into a carboxylic acid. Right? So if you know that already gives you the answer. So if you already know that saponification means make it into a carboxylic acid, what answers are eliminated? C and D for sure. C and D don't make carboxylic acids or anything close to a carboxylic acid, right? So you already eliminate C and D. But you don't even need to know what saponify means. You can look at, they're going to show you the mechanism here. So which one of these mechanistic arrows have you seen when you do reactions with carboxylic acid derivatives? A, B, C, or D? It is, yep. That's right. This is the question. Sorry, I said, I misspoke. It's about saponifying, right? And this is why it's really important to read the directions, because it says what best represents a step in the mechanism, not the final product. So we know it needs to get to acid eventually, but that's not what they're asking, right? Reading comprehension is important. I did that on purpose. Right? So which best represents a step? So which one is the right mechanism that you've seen over and over again? D, addition, right? That's that addition mechanism. And if you look, right, this is silly. What? No. Right, there's a nucleophile. And this is that classic, what I kept harping on you guys about. You can't do SN2 reactions on sp2 hybridized carbons. They're testing you to see if you knew that. Right? And then here, well, this is feasible. That doesn't make as much sense, right? This is going to want to react there first and do that addition, right? So do you need to know the mechanisms? Yes. And do you need to read better than I just did? Yes. All right, number 63. This one asks us which reaction sequence best accomplishes this transformation. So, again, maybe not look at the answers right away. Try to just think about what, retrosynthetically what's happened. So if you look here, if we do some carbon numbering, 1, 2, 1, 2, it looks like we've added a carbon and an oxygen. We went from an alcohol to an epoxide. So this is really asking us to do retrosynthetic analysis, which we practice. All right, it's asking us to do retrosynthetic analysis. So if you have an epoxide, what's the star material that epoxides come from? That's one thing you gotta know. What's the starting material that an epoxide comes from? When we learned about making epoxides, what was the starting material they came from? Not the reagents, what starting material? Alkene, right? It comes from an alkene, right? Remember with alkynes, you always end up with one pi bond left over, or you did that tautomerization, right? So with reactions with alkynes, you always have one pi bond left over, whether it's right in the form of a carbonyl pi bond, like acetyl bond O, the C pi bond O, or CC pi bond. But with alkenes, you have no more pi bonds left. So this came from this alkene. So if I number this carbonyl 3, 3, 1, 2. Right? Now I need to think about what are ways you know how to make alkenes. Right? What are some ways you know how to make alkenes? Where do they come from? This is where it gets tough. Right? There's a lot of ways to make alkenes. Right? So maybe at this point, let's try the forward synthesis. Anybody know what the reagent is? Or what a reagent is that you can use to make an epoxide? You can have it react in acidic and basic conditions, but if you want to make an epoxide, there's one reagent we talked about. You guys knew the mechanism for this even too. This is the perbenzoic acids. So MCPBA. So any of those things that you'll see that looks like this, metachloro, so metachloro, perbenzoic acid, MCPBA, or anything with this functionality, that creates an epoxide, right? Because that one of these oxygens ends up adding to that pi bond of the alkene. Look back at that mechanism, we did that, right? So okay, so you know it has to include MCPBA in that last step. So now at this point, maybe it is worth it to look at the, right? So like, and this is so vague, right? How many different ways can I do this? But I need to add one carbon, it's weird. How do I add one carbon, but also make an alkene? What could I do that from? Right? That's a tough one if you haven't remembered, right? If you maybe remember something about the Wittig reaction, that the Wittig is a good way to add one carbon, make it into an alkene. Remember, the Wittig is the one with the phosphorus. Right, that Wittig reagent. And then you can see from here, this is just an oxidation or oxidation away from doing it. So if you look at the answers, right, SOCl2 would make it a Grignard, right? So you look at the first one, right? This is pretty tough. A Grignard reacting with an epoxide won't end up with an epoxide. Two of the answers include MCPBA at all. So even if you knew nothing else, B and D include MCPBA, so that'd be good answers. And then from there, you look at, well, I don't really understand how an alkene fits in, right? So maybe D looks a little weirder. And PCC, you know, that turns things into an aldehyde. So the answer here is B. Super tough problem, right? Super tough problem. This would be a hard problem on the exam I would give you. This would be like the hardest problem I could give you on exam for that unit, right? Tough problem. Key points: knowing where epoxides come from. They come from alkenes and what that reagent is. That at least narrows it down to a 50-50 shot, right? Number 44 is asking, beta-D-glucose forms a hemiacetal cyclization as shown. Which oxygen is in the ring? So a couple things. Need to remember what a hemiacetal is. That's part of they're trying to get at here is, do you know that this is a hemiacetal? Right? This piece right here is a hemiacetal. Carbon bonded to two oxygens. One of them is an ether, one's an OH. That's a hemiacetal. And it's going to cyclize. So when you form a hemiacetal, or any acetal really, it's when an alcohol, an oxygen, like interacts with a ketone or aldehyde. So one of these three oxygens is going to do an addition reaction, essentially. All right, we're going to do an addition reaction. There's no good leaving groups. That's what's going to cyclize. So the question is, which of these oxygens is it? So right off the bat, you should realize it is not oxygen 1. Oxygen 1 is not in the ring. Now, what they're asking is what oxygen in the starting materials is this one? It can be a really easy problem. Number your carbons and oxygens. That's all you got to do. It looks a lot harder than it is, but really it's not too bad. 1, 2, 3, 4, 5, 6. So I do the carbons first. All right? So the carbon that has two oxygens on it has to be carbon 1, right? Because that's the part, right, we do the addition on, right? So which carbon has the one? That would be this one is 1, 2, 3, 4, 5, 6. So the trick here was, do you know what it was really just asking, do you know what a hemiacetal is? And do you number carbons? But you really got to know this, and a hemiacetal, know that it comes from, or if you see a hemiacetal, the two starting materials it came from were, in this case, an aldehyde, right, and an alcohol. All right? That's what hemiacetal is. So in this case, it would be oxygen on carbon 5, so it'd be 3 would be the correct answer. That'd be the one that is the oxygen in the ring. You need to know what a hemiacetal is. You need to be able to number those carbons. So taking a look at our last sapling assignment, that's our ACS exam prep. So number 3 has 3 compounds, and it says rank them according to highest pKa to lowest pKa. Question basically asks, first of all, do you know what pKa means? A low pKa means what? Acidic. Low pKa would refer to something that's more acidic. What is something that's acidic? In the classic sense of the term, what are acids? What do they donate? They donate, right? They donate protons. That's that Bronsted acid. They're electrophilic, they're delta plus. All right, so that's what they're really, those are the ideas, those are the concepts they're asking. Now, they want you to rank these, so what part of each of these molecules do they want you to look at? What's the most polar bond in each of them? In this one, what's the most polar bond? The SH, the OH, and the SH. There's one other thing that's different over here. There's a chlorine over here. Okay, we're already thinking about that too. Sulfur versus oxygen. Where are they in relation to each other on the periodic table? Sulfur, so oxygen's here and sulfur's here, right? So sulfur's lower on the periodic table in the same period. So what's the difference between oxygen and sulfur? Sulfur is bigger. What does that mean about sulfur's bond to hydrogen? So this is sulfur, and this is oxygen. They're both bonded to hydrogen. Who has a stronger bond to hydrogen? Sulfur or oxygen? Oxygen, right? Why? More orbital overlap. So they're also thinking about, right? Broadly speaking, we're thinking about bonding here and periodic trends. Right? So this is another, right? We're also talking about periodic trends. These are the concepts of this problem. That's what they're hitting on. So which one's going to be the more reactive acid? What's going to have the higher peak? What's going to have the lower pKa? Sulfur, oxygen ones. Sulfur. So the highest pKa would be which one? The oxygen. Now you have 2 sulfur compounds. Which one of these is going to have the lowest pKa? One with the chlorine or one without the chlorine? What's the chlorine one doing? Chlorine's inductively pulling away electrons, making this more delta plus, right? So we're also talking about induction here. So this would be the lowest pKa, because chlorine's inductively pulling away electron density. Good. How else would they ask this question? What else could they do? So right, think about like our concepts: induction, periodic trends, bonding. So you know something about pKa. What if I put a chlorine that's closer? So there's this one, and then I put this one. I had a chlorine right here. Which one's going to be more acidic? Chlorine closer or chlorine farther away? Closer. What if I put a fluorine there instead of chlorine? Which one's more electronegative, fluorine or chlorine? Fluorine. So that's going to be even more reactive, right? So think about ways they could change this question to get at these concepts about induction and about periodic trends in relationship to acidity. Right, so that's how they're going to, right, that's, right, so it's not just enough to know the answer here, but think about, right, okay, how could this question get at these same exact concepts, right, but in a different way?